Hi everyone, good morning. This talk is about network layer analytics with a particular focus on SPI node dominance in the Monero peer-to-peer network. I'm Yanis and I represent ProbeLab. At ProbeLab, we know that decentralized systems, distributed systems do not always work the way you think they do. And at the same time, in the Web3 system in particular, there is a ton of attention paid to on-chain metrics, analytics, and dashboards. But basically, there is very little that exists for the peer-to-peer layer. We feel that the peer-to-peer layer is that small brick on the right of the XKCD graphic, where if that collapses, then all the building on top, all the application, all the consensus, everything is going to collapse together with it. So we believe that it deserves more attention. And that's why we carry out rigorous protocol measurement, benchmarking, and optimization in order to make peer-to-peer networks faster, safer, and more resilient. Now, over the years, to achieve this purpose, over the years, we've built a suite of tools that cover the whole spectrum of the networking stack, starting from network tools for network topology, such as crawlers, to infrastructure and platform monitoring and alerting, and then going deeper into protocol performance, into how things work, in terms of overhead, for example, latency, or any security kind of vulnerabilities that might exist. A tiny bit about myself. From 2024 onwards, we have been building the ProbeLab team as the go-to team for peer-to-peer layer optimizations. ProbeLab initially started as part of Protocol Labs, which is the team that kind of incubated and supported several well-known protocols such as IPFS, P2P, Filecoin, and several others, which company I joined in 2019. So ProbeLab started in there, and of course, in the first instance, focused on IPFS and P2P, but then expanded from 2024 onwards from there to collaborate with several other major blockchain networks. In a previous life, I was an academic. I had great interest in future internet technologies, networks, and protocols for device-to-device communication, decentralized interconnected systems, which is, several projects I carried out at University College London. So what we did and why we're here to talk today. So we know that generally protocols reveal information, nodes reveal IP addresses, handshakes and other node interactions, reveal metadata, peers and peer lists and connectivity lists are generally public. So if you put together all this information of node interactions and protocol interactions, generally behavioral patterns emerge that if you know how to read that, those interactions and the data that come out of it, then they can tell you quite a lot about the network. And obviously, that's not necessarily something that is desired by a community like Monero, where privacy is kind of first order citizen. So what we did is that we adapted Nebula, our flagship crawler, which supports several blockchain networks. We made it quite efficient. It can crawl the network in less than 10 minutes. We collected data to do analysis. Everything I'm going to present here is more than 3 months old, although we've got data from kind of more days, but the data is from the 24th of February. So we wanted to not just count nodes, but try to understand what's going on behind. And that was just the first step. We hope we're going to be able to dive deeper into it. And by the end of this talk, basically, I hope I have convinced you that there needs to be more done at that layer of the Monero stack. And there can be more optimizations brought forward. Now, in terms of methodology, as I just mentioned, we got the Nebula crawler and extended it to execute the Levin handshake, and in order to discover new peers, and the Levin ping in order to verify the identity of a node. The limitation here is, of course, as you understand, it's a crawler, so anything behind the nut is not visible to us. We hope that this will be the major item to investigate next. In terms of spy node identification, we use this simple heuristic that is well known in this community, I believe, the handshake versus ping peer ID mismatch. So if the peer ID between doing the handshake and doing the ping to a node does not match, then this node is identified as a spy node. And then this node is put into a banned list. I'm going to talk a little bit more about the banned lists later, but basically we assume that a node has adopted the banned list if it returns 0 peers from the banned list that we already have. Now, before we get into the results, I'd like to start with a quick quiz. So if I told you that we have discovered 30,000 unique IP port combinations in the Monero network, how many of those do you think are protected against spy nodes? So by raise of hand, who thinks it's less than 2,000? Okay, few people. Okay, maybe more. 10,000? Okay, maybe more. In the neighborhood of 20. Okay, goes down, and then more than 25,000. Okay, very, very few people. Okay, so the right answer is basically less than 2,000, which is quite surprising to me. We see that there is a kind of big slide from 30,000. It's not necessarily nodes, it's unique IP port combinations, but they do something in the network anyway. So from 30,000, we go down to less than 2,000. So already we see that there is a big kind of, some space that something can be done, hopefully an optimization. So let's go and see how we arrived from 30,000 to this 2,000, and hopefully I will have convinced you by then. So in terms of network topology, as I said, it was not exactly 30,000, it's 29.1 thousand unique IP port combinations that we found in the network. And what is interesting here is that we could only connect to 17.2 thousand of those. We could establish a TCP connection, which is a big gap, which we're going to see in the next slide. But to most of them, we could also establish a Levin handshake, which is great. Then there is a big gap that goes down to almost 11,000 discovered unique IP addresses, which already points to some collocation. So more than one node running from one physical machine, or network churn. So a node leaving and coming back and then getting the same IP address or an IP address from the same range. So we already see from this first result that is quite dynamic environment. There is quite a bit of collocation. There is quite a bit of coming and going in the network, which requires further attention, I believe. Now, in terms of connection errors, basically, how do we go from that 29.1 thousand to 17,000? Why did that happen? We see that there is in half of the cases, there is a timeout failure, which means a firewall issue or a node that has gone offline, or basically simply a very busy node that did not manage to respond to our kind of handshake request, which, yeah, is not very likely because our timeout is set to 30 seconds. And the other half is like a connection refused error message, which basically means that the process is not running anymore. So although there might be, there might be some optimizations that we could do on our side, I think that this is a very big percentage that could be, it's basically 11.8 thousand nodes that we could not connect to. There are lots of stale networks in the network, which also could be optimized, I believe. In terms of geographical distribution, we didn't see anything too surprising. It's very common, in other blockchain networks as well. Most nodes are running in Europe and North America. And this is like, at least in terms of a picture of what it looks like. Now, if we go to spy nodes, which I believe is of more interest to this audience, we find that 81.9% of nodes run in the Spruce Creek Networks cloud entity, which is, of course, alarming in terms of centralization. It's a very big percentage of nodes. And like this applies to the nodes that we have managed to establish a 11 connection with. So we're talking about these 16.5K nodes. Now, the more alarming thing is that out of those nodes, 81% identify as spy nodes. So basically, we see that there is 81% of the network running in that one cloud infrastructure, and 81% of the network is spy nodes. So you can make the connection, and although it's a big problem, of course, at least the community knows where the problem is. So again, something can be done about that, I believe. Now, if we go next to the ban lists, so the ban list is something that the Monero community is putting together, following that simple heuristic that I mentioned, the handshake and the ping peer ID. If these two are not the same, it's not the same peer ID coming back from both of these, then the network, then the node is assumed to be a spy node, and is put into a list. This list is then made public, and the node operators are supposed to get this list and not connect to any of the peers in that list. That's what the usefulness of ban lists are. And as you understand, spy nodes do not adopt the ban list because they don't want to ban themselves, obviously. So we're expecting that the ban list adoption is more than that 81% that I mentioned earlier. Indeed, it's 91.5%. But it makes sense to go from this pie chart to the other one where we exclude the spy nodes because they wouldn't adopt the ban list anyway. And we still see that there is 53% of honest nodes that do not adopt the ban list, which leaves us with 46% of 3,000 nodes, which takes us to less than the answer to the initial quiz, about 1.5K nodes that are protected against spy nodes in terms of not being connected to them, not sharing any information, metadata, information about transactions or anything else, which is a very small percentage in my opinion. Now, what does this look like, the big picture? So if you see, so we tried to work with the peer lists and the connectivity lists, and that's what we came out in terms of like topology of the network, or structure of the network, if you want. And we see a very thick red cloud in the middle, which is the spy nodes, and they're very densely connected with each other. Then we see a ring around that, which is the blue nodes, which are honest nodes, but nodes that do not adopt the ban list. And they're very well connected with spy nodes, of course, because the spy nodes will try to connect to them, and they don't have any mechanism to say that I'm not connecting to this node, so they're accepting the connection. And then there is the green cluster there, which is kind of separate, separate from the rest of the two, adjacent but separate, which is the green nodes, which are honest nodes that do adopt the ban list. So it looks interesting. There are lots of nodes around, but these are nodes that probably just join the network. They don't have too many connections in the network, so you can see, green and blue dots all around. But the interesting thing to take away from this is that the ban list technique does work. So you can see that if you adopt the ban list, you're not connected to red nodes. You're connected amongst other honest nodes primarily, and to a few of the blue nodes that are not that are honest nodes, are not spy nodes, but at the same time they do not adopt the list. But there are other questions that come out of this, at least in my opinion, which is what does the kind of week-on-week dynamicity of this last graph I presented, but several other previous ones, look like if we have it monitored continuously? How does this structure of a network affect message propagation and what is called the Dandelion protocol, or Dandelion plus? Do the spy, what's the role of spy nodes? Do they delay message propagation, or is there any privacy implication, or even with regard to the heuristic that identifies spy nodes is not the best that can be had from to identify the spy nodes. And for this, we think that the from the earlier slide, the suite of tools that we have, most of it could be adapted and get more into the kind of weeds of the networking stack. So yeah, with this, I would like to point to a very elaborate study that we did, which is published as a blog post on our website. More information that what I have presented here, of course. At ProbeLab.io, you can see dashboards for many other blockchain networks that we are monitoring and presenting results for. This is my contact details, and yeah, with this, happy to take any questions.
That was really fascinating talk. Maybe while I walk up into the audience, I can start with a question. If someone's running a node on their own machine that's not really accepting internal connections, so essentially just to serve your own wallet, where is that categorized? It's just completely.
It's not shown here.
Yeah.
Okay. Maybe if there was an interaction, it could be the initial 30,000 IP port addresses, but even then, I don't think so. It would need to be different settings.
So it's just like dark nodes, essentially.
Yeah. But we plan to look into this and identify what can we do with unreachable nodes and nodes behind nuts. So it's not going to stay like that forever. It's just more elaborate study that is needed.
Very nice presentation. Thank you. I didn't catch in your presentation how you understand which node is spy node, and second one, do you probably know or suppose why and who is running the spy nodes?
So on the first question is there is this technique. So there is this Levin protocol in the Monero stack, which does two things. You need to establish a handshake, to do a handshake with a node, in which case you get the peer ID of that node. And then you can do a ping, which is like similar to a regular ping that we do in the internet, but using this Levin protocol. And this again returns a peer ID from the other node. If these two are not the same, then this is a heuristic that says probably this is a spy node because there, like someone is running several backend nodes and just responding to requests. This has been a well-known technique in the Monero community. My personal opinion is that it works well, but it could be that it could be enhanced by a second step or something like that. I believe that answers the first question. And the second, what was the second question?
Who is Spruce Creek and why are they doing this?
All right, yes. I don't believe I'm the right person to answer that. I don't know. But there are spy nodes that want to break into the privacy of Monero and basically match IP addresses to transactions so that they can de-anonymize transactions in the Monero network, basically break the privacy. And to do this, you need lots of nodes so that you can listen into as many messages as you can and try to make, this, connect the dots, basically.
Did you do any, did you look into nodes running on Tor or I2P?
Yes, no is the short answer. We might have some very initial data, but we haven't looked into Tor. This is part of our next steps, upcoming agenda.
When you identify nodes running the ban list, is there any false positive? Like if only by chance it didn't connect to any spy nodes?
We haven't, I don't think we have identified or we've seen any false positives. The technique we used is not a great one because what happens is that we're asking for a node to tell us other peer IDs to go and discover other nodes. And I think in this case, they return back to us 250 peers. But of course, their peer list is long, much longer than this. So it could be a few thousand nodes. So it could be that there are 250 by chance that do not match the peer list, and therefore we identify a node as a green node when it's a blue node. But we haven't seen that happening too often out of like repeated times that we've run our scripts.
Thanks. Really nice presentation. You said, well, you used a couple of times the words heuristic, and then you just mentioned in the other question that you're thinking of a second step. So I would like to know how trustworthy you are in just this level of heuristic. If spy node actors could actually break it, and then if you're already planning something next.
Yeah, so I would like, I'm not questioning the efficiency of the heuristic. It is definitely a sound one, but I think we need to, I don't know, scratch our heads a little bit and try to see if it's the best one as well. So it looks suspicious to me that there are all these blue nodes that we saw on the graph, and therefore the question emerged, could these be just proxies of spy nodes in some way to get information from the honest nodes, the green nodes, and then pass them on to spy nodes that are very well connected with them. And I don't know, it looks a little bit off to me.
Great talk. Thank you so much. Two questions. Number one, how exactly can a spy node compromise privacy? So they obviously don't have good intentions, but how do they use the connections they have to compromise Monero privacy? And second, as a Monero node operator, how do I add the ban list?
So to start from the second one, I think it's shared by the Monero community. So the Monero community is running crawls and is putting together this this ban list, and this is made public. So it must be in some GitHub repository. I haven't looked it up myself, but it must be somewhere very public. And on the first question, how do spy nodes try to kind of break privacy? I'm not aware of the details, but basically, if you try, so this is related, I think, to the first talk today. If you have enough data points of transaction messages that you could infer, the IP address, then that the IP address, then you could infer the economic activity, the financial activity of this node. Yeah. So basically, you need lots of data, and perhaps that's why there are so many spy nodes. Yeah.
Thank you for your talk. I was wondering about the behavior of spy nodes. Do they, for the nodes you have identified as spy nodes, do they have a tendency to always send you other spy nodes in the list of peers?
Can you repeat? What is the role of spy nodes? Was the first question?
Do the spy nodes always send you other spy nodes in the list of peers?
No, I think that's random. They could be, if they know and are connected to other nodes, they might send that as well. I suspect. I don't know. I don't know how they operate exactly, but I suspect that there could be nodes from the blue part which do not adopt the ban list and therefore are known to the spy nodes. It could be in their connectivity list. I believe they would share that.
Okay.
Can you repeat? Is the percentage of spy nodes? What is the percentage of spy nodes that is needed to de-anonymize transactions? Yeah, I don't know this answer. Because I don't know the exact thing of how much data is needed and what is needed in order to de-anonymize the transaction.
In order to activate the ban list, you have to put a setting on in your Monero config and download the ban list. And that is why I reckon it's such a small percentage, because it's not on by default. Do you think there's value in pushing the community to put the ban list on by default?
Yes, I believe so. Yeah, definitely.
Not a question. I just found if you are looking for more info on the ban list, you can go to Monero project/meta on GitHub and look for issue number 1124. There's a link to the ban list and more information.
All right. Let's do one more question.
Thanks. How reproducible is the ban list, or do we just have to trust you?
I'm not the one putting together. We're not the ones putting together the ban list. It's from the Monero community, but I believe it's very easy to do, because what you have to do is basically run a crawl similar to what we did, and you can use the Nebula crawler. Is open source. Yeah, and then take each one of the peers that you found and try to go and do this handshake and peer, and yeah, find the results basically.
All right, let's give Yannis another round of applause. Thank you very much.
Thank you.